All right, welcome back. Happy Friday. Today, March the 10th, quiz number 4 is due, so throw it right in the folder right now in whatever state it is in. This is the start of our collection of classes on applications of antiderivatives. The first 3 are going to be about areas and volumes and arc length, all geometry stuff. Then we're going to do a couple of days on physics, density, and work, a day on economics, and a day on probability. All of these are going to be applications of antiderivatives. And after this big section of applications is going to be our second test. All right. Coming up this coming week, we've got a regular full week, but then the following week is spring break. And I mentioned that just because the Peer Tutoring Center is going to be open for peer tutoring over spring break. It is by appointment only, so don't just waltz in, but just go make appointments and meet people like all through spring break if you want. It might be the ideal time to get caught up or get ahead or just be in a really good position for essentially the second half of the semester, not just in this class, but really in just about any of your classes, okay? Really good resource. It is not utilized very much over spring break, so go take advantage of peer tutoring then. Any questions on the calendar? Okay, then let's jump in here on page 34. Today we learn how to measure area or volume of an irregularly shaped object by slicing the object up into easy to measure pieces. So we've already done some area stuff this semester. In fact, you had an entire project where you calculated areas of shaded regions. So you're not going to be surprised to see that to find areas we do antiderivatives, right? We do integrals. But we're going to think about those areas in a different way, and it's going to lead someplace good. So let's give this a shot. Number 1 is related to the project that you are currently working on. The Gamma project is due on Monday. Hopefully we're making good progress there. But I just want to point out that problems 5 and 8 are particularly tricky. And there is a YouTube video that you can take a look at. You don't need to watch the whole thing, just the first 21 minutes, which will help you quite a bit on problems 5 and 8. It's possible you could do problem 5 without any help from that video, but problem 8 really requires a technique that we have not talked about, and is definitely worth your while to watch that, okay? You could also go find the direct link if you just log into Moodle. Also, note on YouTube, you can watch the videos in different speeds. And so if the person talking in that video is talking too slowly for you, bump it up to 1.5 speed or double speed and listen to stuff about the Gamma project from a chipmunk. All right, number 2, recall our definition of the area under a curve. Okay, so I've brought this picture in here. You don't have this picture, I just grabbed it from our first packet, but this is a picture we talked about way back in the beginning of the semester, and we were interested in finding the area under this curve, and so we cut the region into a bunch of pieces, and then we would I'll draw some left rectangles here. And we would say that the area under the curve is approximately the sum of the areas of those rectangles, right? And if we wanted to really get the right answer, we would let the number of rectangles go to what? Infinity, right? The more rectangles, the more accurate, probably. And so we had this this way of thinking about the area of each of these rectangles. For example, let's look at this guy here in red. The area of that rectangle is the base times the height. The base, do you guys remember the symbol we used for the base? Delta t is good. It's just a small change in t. Sometimes t was time. And then the height of that particular rectangle in this picture, you probably can't read that, but this says t0 and then t1 and then t2 is that third point right there. And so how do we represent the height of that rectangle? It's the function at t2, isn't it, right? It's like however high the function is. And so the area of that particular rectangle was the base times the height. Delta t times f of t2, that's this guy right here, okay? Delta t times f of t2, and then you can add all of the areas of the rectangles up. Typically, we would let n be the number of rectangles. And then, as you said, if you want to get the real answer, the right answer, and not just an approximation, you let the number of rectangles n go to infinity. So we've seen all that before, just kind of reminding you of that notation. You guys remember this symbol right here? What is that called? It stands for sum. What's the Greek letter? We don't know our Greek letters?
No, I do.
How are you going to join a fraternity and sorority when you go to a 4-year school if you don't know your Greek letters? Sigma. Sigma. Capital S in the Greek alphabet. Okay, and it stands for sum, and it's just a compact way to write lots of additions like we've got there. So the general pattern for all of these things highlighted in yellow is f of t sub something. It could be t1 or t2 or all the way up to tn, but it's always f of t something and then times delta t. And so we capture that. I'll highlight it in the same yellow. F of t, we're going to call it I times delta t, okay? And all we need to do is let I run from, how much is I in the beginning? 1, and how much is I at the end? N. And so that's this thing here in blue, I equals 1 to n, okay? So that's sigma notation, just a compact way to write that big old sum. And then I'll highlight in green again, the same limit as n goes to infinity, okay? All right, so here's the point. And then at the end of the day, we said, hey, we're not going to write all of that stuff because it's very long to write out. So we're just going to symbolize that with this integral symbol. And it just stands for the area under a curve. But the point of all this is that if we see something like this right here, some function multiplied by a delta t inside of a sum, inside of a limit going to infinity. If we happen to see that, then we are going to think, okay, I can just write the integral, all right? And we're going to see that today in the case of an area problem first, but then we're going to start to see it creep in with some volumes. And in the next few classes, we're going to see it creep in work and density and lots of other applications too. We're going to start to recognize this thing of underlined in red. When we see something that looks like that, we get to write an integral. Evan. So n is the number of rectangles, right? Yeah, n is the number of rectangles. It's you can't see it, but that's t sub n is the last thing here. Yeah, so we just let n be the number of rectangles. Ti is a generic t value in between. Yeah, okay. All right, so the point, like I said, we can convert certain Riemann sums, that is, those kinds of sums underlined in red, into corresponding integrals. And now we know if we have an integral, it's a matter of finding an antiderivative and plugging in top and bottom and subtracting, or if we can't do an antiderivative, typing the integral into the calculator. All right, so let's take a look at number 3. We're going to find the area of this triangle right here. Okay, so this is nice because it's really easy, right? What is the area of this triangle? Half base times height, so what is it? Half of 6 times 3, 9? Right, 9 is the area. Okay, we're going to answer this really easy question in a really hard way. And we know the answer is 9. And even though we already know the answer, you got to trust me, we're going somewhere good with this much harder technique to get the same answer of 9. Let's give this a shot. Okay, we've got our triangle. We are going to cut this triangle into a bunch of teeny tiny little slices. There's one right there, that vertical slice. We are going to think of that vertical slice as being approximately a rectangle. It's not that far from being a rectangle, and the thinner this slice is, the more closely it is to being a rectangle, right? It's never really a rectangle, but we'll think of it as a rectangle. And so I'm going to start writing here the area of that one slice. I'm going to use the generic term slice. In this case, it's a rectangle-ish. Is base times height. Okay, let's see. So the base times height. What's the symbol for the base of that slice? That's delta x. It's written down there. I don't have a symbol for the height of that slice. So let's give it a symbol. If you were going to think of this vertical height as being an x or a y, which one seems more natural? How about a y, right? I mean, it's a vertical up and down kind of thing. Okay, so it's delta x times y. Fair enough.
Why wouldn't we use trapezoid?
In this case, a trapezoid would give you the exact answer. And that's even better than what we are doing here. But the point is that these things are going to be curvy in just a second. So like hardly ever will we be able to do the exact answer. We're just going to think of everything as being rectangular. Okay, so it turns out that you cannot deal with more than one letter sitting in this expression right here. We'll see why near the end of this problem. And whatever letter you choose to put next to the delta, that's the letter that you are saying this whole thing is going to be. So we're choosing x. So I got to get rid of this y and replace it with some corresponding x. taking a look at that picture over there, do you guys agree that this little triangle here on the right is similar to the big triangle over there? And you guys remember we can write a proportion when we have similar triangles? So let's write a proportion. For example, I can say that y is to, what's the corresponding thing in the big triangle? 3. As, okay, and now in the little triangle, x is to 6. Everyone agree? Remember I said we are committing to whatever letter is after the delta, which is x in this case, which means I want to solve that equation for what letter? I want to solve that equation for y so that I can then substitute for this y right here. So solve this equation for y by multiplying by 3. Y equals 3x over 6, or y equals 1/2 x. Good? The y is always half of the x in that picture. Okay, so then we can take that thing and plug it right back up here. Equals delta x times 1/2 x. It's okay. That's better than what we had with the y in it because we only wanted x in this expression. Okay, that is approximately the area of one slice. In fact, maybe I shouldn't have even said equals. I mean, that equals right there. It's approximate, right? It's not exactly a rectangle, but it's close enough. Okay, next up is to approximate the area of all the slices. Area of all slices. Approximately equal to. Okay, I am going to imagine taking this horizontal line and cutting it up into a bunch of pieces, x0 and x1 and x2, and maybe this particular one that I'm looking at is x3, doesn't much matter, all the way to xn at the end, okay? And so this 1/2 x should really have been 1/2 of x3 in the picture that I've drawn there. It's really the third x that I'm interested in. But in general, it's always going to be this expression, and there's just going to be a little subscript on this x right here that's going to change from beginning to end. And so all we're going to do is rewrite that thing inside of a summation. I'm going to copy it just like it is, delta x times 1/2 x. Right, that's that thing up there on the top right. The only twist here is that I'm saying, hey, there's really little subscript of I right there. That x is just going to change, it's going to sweep out the entire, that little slice, the rectangular slice is going to sweep out the whole triangle by letting x change, x1, x2, x3, x4, x5, okay? And the delta x is just a particular distance, like maybe it's a, 1/2 centimeter or something for, yeah, it's a unit. Okay, and then we're always going to do I equals 1 to n, that's just standard. And so then putting it all together now, the area of the triangle, the given triangle, is equal to, I'm copying that whole summation just like it is, delta x 1/2 x sub I. But what are we putting in the front here to really make it so it's perfect? What is it? It's going to become an integral in a second. But what are we putting in front of this summation? It's a limit, right? We got to make sure that we let the number of rectangles go to infinity. Right? And then the fact that I called that thing a rectangle, that little vertical slice, even though truly, as Nick points out, it's a trapezoid, the fact that I called it a rectangle is going to become irrelevant as long as I let the number of rectangles go to infinity. Okay, so that is the true area of the triangle. And as Tala points out, anytime we see this exact kind of formulation with a limit and a sum and then a pattern inside of there with a delta x, oh, that's just the definition of an integral. The only difference between what we've just written And what's highlighted up here, or what's underlined in red, let's take a look at the pieces. Do we have this, this limit in the front of our thing? We got that. Do we have a summation from 1 to n? We got that. Do we have a delta t? Yeah, it's x in this case. We have that. The only thing that is ever going to change is this function. We just have to identify what the function is. What is the function? 1/2 x. That's the function. That's the only thing. So what we get to do is put 1/2 x right inside of an integral, and that's it. And so I've got an equal sign here, and I really mean equals. It's not an approximation. It's equal to the integral of 1/2 x dx. And I'm going to circle on this delta x, and I'm going to say that became this dx right here, right? They're almost, I mean, they're the same, right? Greek delta, r, letter d. It's the same. The idea there is that that delta, the dx stands for this little width. And then I'll circle in red here, the 1/2 xi became the 1/2 x. All we need to do is put in the limits. As you take this guy and sweep, what's the, how much is x at the beginning? Taking a look at your picture, x is this distance, this horizontal distance. How much is x at the smallest? We're trying to sweep out the whole triangle. 0 at the smallest, and how much is x at the biggest? Not 3. It's 6, right? It's that whole, right? So x is going to sweep from 0 at the far right to 6. So we put a 0 and a 6. Everybody see where those numbers came from? Okay, and now we finish. We're at the antiderivative step. This one happens to be really easy. 1/2 can get factored out. The antiderivative of x is x squared over 2, going between 0 and 6. It is going to be a 1/4. When we plug in 6, we get 36. When we plug in 0, we get 0. Nine. So what's the area of the triangle? 9. Hooray. It's 9. Okay, I promised you we were doing an easy problem in a very hard way. Probably you believe me now, but this is going to allow us, this technique is going to allow us to solve some hard problems. We could only, very fortunately, find the area of that one easily because it was a triangle. There's very few shapes we can actually do. Let's try number 4 here. Okay, same Riemann idea. To find the volume of this solid right here, we'll use the calculator once we've gotten to the integral. Okay, so here's our picture. What's the name of this shape right here? Circle is a 2-dimensional thing. This is a half of a what? That's half of a cylinder, right? Okay, so actually, it turns out there is a formula that some of you might know for the volume of a cylinder. What is it? Yeah, so I'm going to write the whole cylinder as pi r squared h. That's the volume of the whole cylinder, but Nevin points out there's a half because we only have half of the cylinder. Okay, let's get it right here. 1/2 pi. How much is the radius? That's the 7. 7 squared. How much is the height? Is the height 7? The height is the 10. In fact, that vertical 7, I didn't even need to tell you because it's the same radius. Yeah, you can tilt this thing if you want it to really look like a cylinder the way you'd expect it. Okay, so let's just get a number up here. So this is 7 squared is 49, times 10 is 490, and then half of that, 245. I think it's that. 245 pi. That's the answer. Okay, again, we're going to solve an easy problem in a hard way. Okay, let's start. The volume of one. Okay, that little thing that's kind of floating in between the top section and the bottom section, that middle thing, you can call it a slice. For volume things, I'm probably going to call it a slab. but you're welcome to call it a slice every time. Okay, that floating thing in the middle there, I don't know how to find the exact volume of that. That is a curvy shape that it's complicated. But can I convince you that it is approximately the same shape as a shoebox, like a length and a width and a height? If everything, like it's curvy, right? I mean, it's curvy because of the circle. But if that thing is really, really thin, then the difference between, you know, like where it is at the bottom corner and where it is at the top corner is not, it doesn't curve that much if it's a really, really thin slab. Buy it? It's approximately a shoebox in the same way that the slice up above was approximately a rectangle. Okay, what's the volume for a shoebox? Perfect, length times width times height, right? That's what we're going to use. Okay, equals. Okay, let's skip the length for a second. I'm going to put some parentheses here. That's going to be our length. The width, what is the symbol for the width of this, the width of the shoebox, which I would say is this distance here. That width is 10. It's always 10 going this direction. So the width is 10. And how about the height of that shoebox? That's called delta y. Great. So the complicated thing is the length of the shoebox. Now you got to imagine not just this particular shoebox, but imagine the shoebox that's right below this one or the shoebox right above it. What's happening to the length? Static or changing? It's changing. And so we're going to have some varying thing inside of here. Okay. All right. Let's take a look. I am going to call this distance from here to here. I'm going to call that x. It's a horizontal distance. I'll call it x. The length from there to there is 2x, yes? Okay, so x is just a temporary holding thing, but 2x is ultimately what's going in the parentheses there. If I were to put 2x in there, we'd immediately recognize we got to change that letter because again, whatever is after the delta, that's what we commit to. So it's got to ultimately be y's in here. So we're holding off. You could put a 2x. I'll put it up above here. But ultimately, it needs to become something with y. Okay, turns out to solve this guy, we need to draw in just a tiny bit more stuff. We're going to draw from here to there, and we're going to draw from here to there. In fact, let me draw that thing first, and then I'll label my x. Okay, so x is that. Okay, that right triangle right there. The vertical length is changing, right? All the different slabs are at different heights. But it's got a letter. It's already got a letter labeled in this picture. What is that vertical? That's the y. Right? It's out here on the left. How about the hypotenuse of that triangle? You could put square root of x squared plus y squared, but it's 7, isn't it? Always 7. Not just for the slab that's drawn here, but even a slab a little lower or a slab a little higher. That hypotenuse is just the radius of the circle, which is constantly 7. Okay, now remember, we're trying to get rid of the x. So we're going to write down our Pythagorean equation here, and then we're going to solve for x. So we know x squared plus y squared equals 7 squared. So that means that x squared is equal to, that's a 49, and then subtract the y squared. And so then x is the square root of 49 minus y squared. So then what do we get to put in the parentheses over there for the entire length? Square root of 49 minus y squared. What else? Times 2, right? Because x was just half of the length of the whole shoebox. So that's what we put here. 2 square root 49 minus y squared. That's good. Okay, that's the hardest part of the problem, is getting to that setup right there where you have only letters y, only y's, y there and a delta y there. We're going to go through the rest of this a little bit quicker than we did above, but you're going to see it's a fairly automated process. The volume of all the slabs is approximately, all we're doing is sticking what symbol in front of this expression? A sigma. We're just adding up. You know, it's not just that one slab's volume, but we're just going to add up all of that stuff over and over again. 2 square root 49 minus y squared times 10 times delta y. I am going to be looking for you to stick the letter I inside of this thing. It's really easy to put it in the right spot as long as you know where it goes. It always goes on the variable by itself, which is what letter? Which is a Y. So it goes right here. It does not go on the delta variable. It doesn't go there because delta Y is going to be the same every time, right? You're not numbering the delta Y's. The width is going to be consistent. So just put it on the variable by itself, right there. And it is always going to be I equals 1 up to n. Always the same. This step is very routine. Just copy your thing from the previous answer, put a sigma, and slap the I in the right spot. The next step is also routine. The volume of the solid, that's the whole semi-cylinder, is equal to, so it is all of this with a little bit of space. Summation I equals 1 to n, 2 square root 49 minus yi squared times 10 delta y. With just a tiny bit of space in the front. What's going in that space? Limit. And goes to infinity.
Are we writing y sub I because it's sort of
what I'm imagining with that y sub I haven't written it out here, but I'm imagining that this is one particular slab, but really what I want to do is I want to take this vertical distance right here, and I want to call this point at the bottom y0, and this point right here y1, and this point right here y2, and ultimately at the top is a y sub n. And so I'm just numbering the slabs. Yeah, and then it's the sum of all those. Yeah. Okay, and then the next step is also routine. If we happen to see exactly this kind of pattern with a limit and a summation and a function and a delta y, what does it become? It becomes an integral. And so this thing right here equals integral. All right, lots of this stuff gets copied. 2 square root 49 minus y squared. Notice that when we go from the sigma to the integral, what did we just drop? What did we lose in here? The I. It doesn't make sense to, like, we're not numbering them in here anymore, right? So we drop that. The delta y changes very slightly. dy, right? Delta y becomes dy. It's a very small change. The limit and the sigma get absorbed in that integral sign. The only thing left to put in there is what? Yeah, we just need the limits. How much is y? Y is this vertical distance. How much is y at the bottom? 0 at the top? 7. 0 to 7. It is a circle function with the height of the cylinder multiplied in there. Yeah, absolutely. Okay, I'll do this on my calculator. You don't need to do it on yours. Let us get an answer here. It just happens, so that integral is hard, math 9, so we're gonna let the calculator help us out here. So we're just typing that whole thing in, 2 square root 49 minus y squared, close parentheses, times 10, and then I think that's it, right? And then comma y, comma 0, comma 7. I think I typed that right. Okay, we happen to know what the right answer is for this one. What was the right answer for the volume? 245 pi. That's what we're going to compare whatever this thing is to. We're going to get a decimal, 245 pi. Good. Not bad. Okay. Yeah. All right, next page. Okay, this next problem here is concerned with finding the volume of a solid with known cross-section. Here is a warning: cross-sectional volume problems are typically hard. They are well known to be nightmare-inducing. Let's give this one a shot. We're going to find the volume of the solid, whose base is the region inside of the circle x squared plus y squared equals 4, and whose cross-sections perpendicular to the x-axis are squares. Okay, So we're going to try to envision this. I'm going to do my best to draw it. Yeah, so we gotta work on understanding what's going on here. So don't draw this. Don't draw this, but here's our XY axes. That's a circle centered at the origin and whose radius is what? What's the radius of this guy? Right, isn't it normally x squared plus y squared equals the radius squared? So the radius there is 2. So then that circle right there is centered at the origin. You're not drawing this yet. And the radius here is 2. Good? And then we are going to imagine creating a solid, a 3-dimensional figure, by taking this as the base, and then the solid is going to come out of the board towards us, and the cross sections, we're going to have these cross sections coming out of the board. And for example, for that particular slice, which is perpendicular to the x-axis, you're going to have a square coming out of the board, however long that is, maybe that's about a foot, comes out of the board, and then makes the rest of the square. What about this square? Coming out of the board a lot less because it's got to be a square. So maybe this one only comes out of the board about 4 inches. And then this guy right here comes out of the board about, 14 inches or whatever it is, and then makes the square. Okay. It's going to be hard to draw it in this perspective because the thing I want to draw is coming directly out of the board. So here's the technique. I make no guarantees that but we're gonna draw our best shot here, and then I'm gonna show you like a computer generated image, which will look a lot nicer than this one. I'm gonna take the x and y axes, but I'm gonna try to draw the y axis flat on the ground. So this is my way of kind of swiveling the y axis so it's more flat. Then I'm gonna draw my circle. So do try to draw this thing here. Okay, and there's my circle. Again, trying to think of it as being flat on the ground, going out to 2's. All right, that's probably as good as I'm going to get. Okay, so the radius is 2. I'm just going to draw a couple of cross sections. So for example, this guy right here, cross section perpendicular to the x-axis. I'm now going to draw a square coming out, like up, like out of the board, but up. So it's going to come up this way, and it's going to come up this way. That's not looking so good. Come up this way and come up this way. I'm really terrible at this. I apologize. Nice thing is you can check out this video on YouTube and show your friends. Look how awful this drawing is that my teacher drew. All right, so square coming out of the board. This is going to be like a Dr. Seussian kind of shape where like the things are not quite right angles. And then if I were to do this square right here, this is going to be the biggest square coming out of the board. So up and up and something like that. Boy, this is like really like one of the worst ones I've ever done. I apologize. All right, and so we've got all of these squares, really small squares at the far right, getting bigger, bigger, bigger until we're in the middle, and then getting smaller, smaller, smaller to the left. And you imagine a shape, a solid, created by all of these squares. The height of the squares is absolutely changing because they have to be squares. They're squares. No, they're squares. Despite what my picture looks like, they are squares. All right, let me show you what this thing really looks like. It's this. So here's your base. There's your circle. There's a bunch of lines that are supposed to represent our cross sections. You can see the square shapes right here, really small squares near the end, near 2, getting bigger and bigger and bigger, and then the tallest squares are right here in the middle, and then getting smaller, smaller, smaller on the other side. Cool? You get kind of like these 2 lines that are connecting all of the vertices of the squares that are up here at the top. All right? So we are going to find the volume of this shape right here. Anybody happen to know a formula? Like we know a formula for the area of a triangle and the volume of a cylinder. Anybody know a formula for the volume of this shape? Me neither. All right, so finally a problem that we're doing in the hard way, but it's the only way we have. Okay, so here we go. Volume of one slab. Okay, I'm not going to add another thing to my terrible drawing over here, but imagine this red square on the right-hand side, and I'm going to give it just a tiny bit of thickness. So imagine drawing like another copy of that red square, like 1/2 inch to the left of this one. And so I'm making like a shoebox type shape. Is that all right? So it's not just a square, but it's going to be a three-dimensional thing. And so the volume of that slab is approximately length times width times height, right? Shoebox. Okay, let us label this point right here with an X, comma, Y, right? It's just a generic point on the circle. Okay, the length of the square, that's going to be here to here. Let's call that the length right there. Would you say that the length is related to X or is the length related to Y? Yeah, this is definitely a Y thing, right? Is this Y? No, Y really represents the distance from the X-axis to the point. So it's really 2Y. Okay, good. So the length is 2Y. Okay? Nick, is that all right? Like if you have a point, 7 comma 1, what does that Y really mean? The Y really means you are 1 unit away from the X-axis, but the distance that we wanted was actually from here to here. All right, so the length is 2Y. Let's go to the height. Height is going to be this distance right here. What is that? It's a square. It's also 2Y, right? I mean, it's not naturally anything. It's coming out of the off the XY axis, but it's a square. So that is exactly the same as that. So it is another 2Y for the height. And then finally the width. Okay, so the width is not really pictured here, but the width is just this little tiny change. I haven't drawn it in, but I'm imagining that that square has another partner square right next to it. So it's just this little pancake type thing. And what's a good symbol for that little change? Would you call that a delta X or a delta Y? That's a delta X, right? So change in the X-axis. So we got that. Okay, I'm going to multiply this thing out. 4y squared delta x. Okay, I don't like having two letters here. X and y is no good. Which one are we committed to? X, whatever's after the delta, that's your choice. So we got to get rid of this y. How are we going to get rid of the y? Well, good news for us is that we have exactly the relationship between the x and the y for that point right there. It is x squared plus y squared equals 4. You don't have to draw like a similar triangle's proportion. You don't need to do a Pythagorean theorem. You need an equation and you have one. It's right there. So we're going to change this y by solving this equation for y. So does everyone agree? Solve that equation for y, you get root 4 minus x squared. Okay, so that means this guy becomes 4 times square root 4 minus x squared. Right? And then we're gonna get rid of that, and yeah, we'll simplify it right now. Right? So we're just changing the y, copying everything else. So this simplifies 4 times 4 minus x squared delta x. Good? Okay, this demo has already gone too long, so we're going to skip right ahead to the integral. So we're not going to write the summation step, we're not going to write the limit step, but we're just going to jump right to the integral from here. Let's say dot, 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 volume equals the integral. It's just that, 4 minus x squared, small change, delta x becomes dx. And then you just have to think about what x is at the smallest and what x is at the biggest. So the smallest x in this picture is way out here at the left. How much is x? -2, and the biggest x is at the right, 2. Those are your limits, -2 to 2.
Is it okay to simplify that?
Yeah, You could distribute the 4. You could also pull the 4 outside of the integral. That's probably what I would do. Again, just to save time, we're not going to do the antiderivative. But can you agree that that is a ridiculously simple antiderivative to calculate the volume of that insane shape that we started with? Right? It's like I could have given you this on the first day where we did antiderivatives, right? Like it's the most basic antiderivatives we could do embedded inside of this ridiculous shape. Okay, so you do your calculation, you get your volume. We're going to make a conclusion here. Take a look at, let's see, take a look at something. Can you tell me real quick? We said that this here was a 2y, right? And this was also a 2y, yes? And if you multiply those two things together, whoops, 2y times 2y, aren't we calculating the area of that square? Yeah, it's just the area of the square. And so that 2y times 2y is right here. So those purple underlined things just represent the area of the square when I multiply it together. And yeah, the y is changed into something with x's in it, but it was just the area of the square times the delta x. It's the area of the square times the dx. And so it turns out anytime you have one of these cross-section problems, there's a really easy way to just jump to the answer. I'll write the formula here. This is the area of a generic cross-section. In this case, it was squares, right? And so that turns out to be true anytime you're doing a cross-section problem. So here's a volume formula in number 7. If for each x, the cross-sectional area of a solid perpendicular to the x-axis is given by a of x, that's just supposed to represent an area formula for a generic x, then the volume of the solid is just the integral from a to b of the area formula dx. That right there, the thing underlined in purple, that's just an area formula, right? It's the area of a generic x, the area of that cross-sectional square. So it turns out that's always the conclusion for cross-section problems. Well, you have to build it. We built the area formula by thinking of it as a 2y times a 2y, and then we did some substituting to get rid of the y. Yeah, so you're not supposed to like just look at that shape and say, oh, the area formula is always blank. That's the hard part. But once you've built the formula, you can just throw it inside of an integral. Yeah. Okay, so the process that we followed is written out here. You can use it as a reference during the activities and or during the homework, but it's always the same steps. Ultimately, the toughest part of this process is drawing a good picture and then coming up with a formula that's a function of one letter only. Once you've got that, the rest is fairly routine. At the very end, you calculate the integral. If you can do antiderivatives, great. If not, I'll tell you to just type the integral into your calculator. Okay, so the activities start on the next page. You can see these problems are time consuming. There are 5 problems in the activity. I don't imagine I've left you enough time to do them, but let's see how many of those 5 we can get through.